All right, welcome back, everybody. Today we're going to be doing section 6.5, which is all about exponential growth and decay. So in the last section, we were talking about the exponential function and we were talking about the logarithmic function before that. Now what we're going to do is we're going to just explore some applications of exponential growth and exponential decay. So let me pull up the slides and we'll get started. All right, so before we begin, we're going to talk about proportionality and just what that means. Then we'll get what's called the law of natural growth and decay. Then we will look at population growth, then radioactive decay, Newton's law of cooling, and then we'll finish up with continuously compounded interest. And that's where we're actually going to derive the continuously compounded interest formula. So let's get started here with proportionality. So what does proportionality mean? Well, two quantities x and y are said to be proportional if there's a non-zero constant k, a real number k, such that y is equal to k times x. So this is what it means for two things to be proportional. Basically, if you want y, you take x and multiply it by some number k. K could be any real number, or any non-zero real number. So like 2, 4, 6. It could be negative, it could be irrational, it could be rational, it could be any real number as long as it's not zero. And that number k is what we call the proportionality constant, or the constant of proportionality. So that's basically the number that relates the two proportionally. So what's the law of natural growth and decay? In a lot of phenomena, both real and imagined, meaning like what you also think in your head, a lot of times quantities will grow or decay at a rate that is proportional to their size. So in other words, if you've got a function that models your phenomenon of interest, it's pretty common for the rate of change of that model to be proportional to the output of that model at that moment. So basically dy dt equals k times y, or y prime equals ky for some non-zero k. And that's basically the idea. So this is what's actually called the law of natural growth and decay. So this equation is what the law of natural growth and decay is. This is actually an example of a differential equation because there's an unknown function y that's related to its derivative by an equality. So I know that some or many of you are going to end up taking differential equations later, which is a really fascinating subject, by the way, and I recommend everybody take it. And you're going to basically spend a lot of time solving differential equations. And how they begin is you basically have a relationship that describes how your function changes, but you don't know what the original function is. You just know like how it's actually changing. And then you can use that information to recover the original function. And again, there's a whole course on that. There are several courses on that. It's an entire field of mathematics, differential equations. So let's think about this one. This is like the first time we've had to do something like this. What could a solution to this differential equation be? This one right here. So in other words, can you think of a function whose derivative is, this is its derivative, right? Can you think of a function whose derivative is just itself, maybe multiplied by some constant? I'll give you a second to think about it, but what do you think could be a function that has that property? Hmm. A function whose derivative is itself, except maybe multiplied by a constant. Okay, well, I think I have a good guess, and maybe you have a good guess too. Let's just guess that it's this function right here. Maybe this is a little bit like what you were thinking, but let's say it's this one. Let's just see if this actually works. This is just a good guess. If this is our function y, c times e to the kt, then when we differentiate it, we're going to get this. Because you remember from the previous section, the exponential function is the function that is its own derivative. So picking that it would be e, or the exponential function in some way, is a pretty good guess because that function is its own derivative. And it turns out that indeed this family of functions here is the solution to this differential equation. There we go. There we go. So if you remember from the last section, I said that the exponential function is the only function out there that is its own derivative, but it's only up to scalar multiples of the input and the output. And this is why. So here, if you multiply by c, you'll still get the same result. When you differentiate, you're going to get the original function. But also, if you have a constant term in the exponent, so in the argument of the exponential function, that will still give you the same result. You'll get the same derivative. All right? And so that leads us to this first theorem. It turns out that the only solutions to this differential equation are the exponential functions of this form. There we go. These are the only functions that are the solution to this differential equation. One little note I want to make. Y of t is the output of this function. T is the input of this function. And here, instead of writing c, I wrote y of 0. And the reason for that is when you substitute 0 in for t to this function, then you automatically get c. So whatever this value is, that's what c is equal to, and that's why we call it the initial value. It's the value that you get when t is equal to 0, whatever t is going to represent. All right, now let's first talk about population growth. So let's see how we can use this exponential model to model population growth and see what we can do with it. All right, so let's start with a population function. So let P of t be the size of a population at time t. We're going to assume that it is greater than 0, so we at least have some population. And if we assume that the rate of change of the population is proportional to its population at any given time, then the law of natural growth yields that this is the relationship that must be satisfied. So once again, we're just saying that how quickly the population changes is directly proportional to the current population at any time. And that kind of makes sense, right? Because if you've got a population, then how much is it going to change? Well, it's going to depend on how much stuff is there, how many people are there, how many rabbits are there, whatever, right? Now, if you move things around a little bit in this differential equation, you'll find that you can write p prime over p is equal to k, essentially just solving this differential equation for k, right? And what you find out is that the constant k, the constant of proportionality, is the population rate, or I'm sorry, the growth rate divided by the population at that time. That's what it is. So that's what k is. K is basically rate of change of the population divided by the population amount. Okay, so what is this special number k called? This number k is what's called the relative growth rate. So it turns out that that constant of proportionality is what's called the relative growth rate, meaning that it's relative to the population, right? And what is it? It's just the rate of growth per population size at any moment in time. So that's how you can find it. Just do basically p prime divided by p, and that will give you k. All right, so let's try this problem. Let's use the fact that the world population was 2,560 million in 1950, and then 3,040 million in 1960. And we're going to use that to make a model of the population of the world for the second half of the 20th century, meaning basically after 1950. We're going to assume that the growth rate is proportional to the population size. All right, so this is an assumption we are making about our model. It's not necessarily the reality of the situation, but it's an assumption that we're going to make for our model because it's a pretty good model to use. So first question is, what's the relative growth rate going to be? And then we're going to use that model to estimate the population in 1993, and then to predict the population in the year 2025. All right, so here we go. We're going to let t be equal to 0 in the year 1950. So we're going to measure time in terms of number of years since 1950. And we're going to measure the population in terms of units of millions of people. So P of t is millions of people, and t is how many years since 1950, right? So based on the information we're given initially, we know that the original population, the initial population is 2560. And then 10 years from then, the population is 3040. That's just using the model that we've set up. Since we're assuming the growth rate is proportional to the population, theorem 1 asserts that our equation has to have this form. So this is the law that the population must obey. P of 0, the initial condition, the initial population times e to the kt, where k is some relative growth rate. Right? So this is where we're at to start. Now, we don't yet know what k is, but we can use the other information that's been given to us to solve for k. And that's what we're going to do next, because we don't know what this thing is just yet. So since we also know that the population after 10 years is 30-40 million, we can plug this information into our model and use it to solve for k. So the output is 30-40, and that's at time 10. So we plug in 10 for t in all instances. And now the only variable that we don't know is k. So we're just going to solve for k using good old algebra and then using good old the definition of the logarithm and laws of logarithms as well. So divide both sides by 2560, write it in logarithmic form instead of exponential form, or take the log of both sides. And then you get this, and then you can solve for k. Now at this point, this is the exact value of k. So you can leave your answers in this form. And in a lot of senses, you really just should leave them in this form, because this is exactly what k is equal to. After this point, your only choice is to approximate. So if you wanted to just get a decimal representation instead of something that's a little more complicated, then you can go to a calculator or a computational resource and it will approximate this irrational number for you. So I did that right here. And we got that k is approximately 0.017185. All right, so we'll use that. We'll use that. That tells us that the relative growth rate is about 1.7%, and we can choose our model to be this, just like so. Okay, now that we have the model, we have the initial population, we have the relative growth rate, we can use this to predict what's going to happen in 1993 and 2025. We just plug in those values of t to our model, and then an estimate would be 5,360 million for the year 1993. And then here, plug in 75 for the year 2025. That's 75 years after 1950. And our model estimates that there will be 9,289 million people. There we go. So that's how this works. That's how the population models work. I kind of mentioned it as I went along, but I just want to emphasize this. This is an important thing to keep in mind as you go forward in, in your careers, in your math education. This is just a model. So this is a model. It is not a guarantor of fact. It does not mean that this is exactly what the population will be, for example, in the year 2025. It's just a model that we're using to try to get an idea of what the population could be based on a pretty natural phenomenon known as the law of natural growth and decay. So we're basically making some assumptions. We're assuming that the population is going to have this behavior, and based on that assumption, we are able to estimate that this will be the population at these times. So just one thing to keep in mind, one thing to keep in mind. Okay, all right, so now let's talk about radioactive decay. So for radioactive decay, this works by, well, an interesting physical principle, which is just that radioactive substances decay spontaneously when they emit radiation. So we can figure out a way to model how much stuff is left after a certain amount of time. So let's let m of t be the mass that remains from an initial mass, m sub 0, of a radioactive substance after time t. All right. Now, it turns out that through experimental observations, physicists have realized that the relative radioactive decay rate is constant. So what that means is when they measure how much stuff is left, and they've done this many, many millions of times, they've discovered that the decay rate is actually a constant. So the relative decay rate is a constant number that does not change. So what that means mathematically is that this number has to be a fixed constant. In other words, the rate of change of the mass, the amount, divided by the mass itself is the same number every time. It's a constant. And in this case, k is actually going to be a negative number. And it's a negative number because the amount is decreasing over time. So it's not increasing, it's decreasing. As you let this substance just sit, it decays and decays and decays, and there's less stuff there, right? So that means the relative growth rate is negative. It's decay instead of growth. All right. Now, again, by theorem 1, by the law of natural growth, we can model this phenomenon as the mass at any time t is given by the initial mass at time 0 times e to the kt for some relative growth rate k, right? because some of these substances have really, really long, uh, because some of these things decay very, very slowly, I should say, physicists often like to express the rate of decay in terms of the half-life of a substance. And what is the half-life? So if you've ever heard of that game, or if you've seen this symbol, lambda, before used in that context, the half-life of a substance is just the time required for a quantity of that substance to reduce to half of its initial value. So in other words, like how many years does it take for an amount of this substance to decay to half of what it started with? That's the half-life. That's the half-life lambda. All right? Okay, so let's try this example just to get our hands dirty a little bit. It turns out that the half-life of radium-226 is 1,590 years. So if we're given a sample of radium-226 that has a mass of 100 milligrams to start, let's find a formula for the mass of the sample that remains after T many years. Once we have this model, we're going to use it to find the mass remaining after 1,000 years. And then we're going to see how long it will take for the mass to reduce to 30 milligrams, right? So we're starting with 100 milligrams. It's going to decay. We know the half-life of the material, and we're going to figure out how much will be remaining after 1,000 years. And then we're going to see how long it takes until there's only 30 milligrams left. Okay, so for this one, what I want you to do is I want you to think about it for just a moment and see if you can think about how you would begin. How would you begin solving this problem? Okay, now say something out loud to your dog, your sister, your brother, your parents, the wall, just yourself. Just say something out loud to give your brain that feedback. All right, now try to work it out on your own, and we'll do it together in just a moment. Let me give you a little bit of a tip for how to start. See if you can find the relative growth rate K. That's a good place to start. See if you can find what K is going to be. All right, now let's do it together. So let's see, what do we know? We know the half-life, and we know that the relative decay rate is going to be constant. So again, by that theorem and the law of exponential growth and decay, this is the model we can use. This is the model we can use. So the initial amount is 100, and it's going to be decaying by some amount that depends on this k. So now we have to find k. And the way that we find k is using the other information we're given, that the half-life is 1,590 years. So remember, the half-life is how long it takes for the initial amount to decay to half of that amount. So in other words, it'll take 1,590 years for this sample to decay to 50 grams, But just with that information, that will tell us what the relative decay rate is going to be. Here we go. So we're going to plug in, what do we know about the half-life? It's this much, right? So that means that the amount left after that time is going to be half of what we started with, which is 50. There we go. So now we have almost a second data point, right? We have a second data point for this model, and we can use that to solve for k. So we know that 50 is the amount of mass that remains after 1,590 years. So we plug that in for t, and now we can solve for k. So just doing some simple algebra, we get to this point. Then we can write it in logarithmic form, divide both sides by 1,590, and we get this. So this is what k is equal to. One small little note I'm going to add here. Let me do this. When I went from this step to this step, I rewrote the natural log of 1/2 as, as 2 to the negative 1, as negative ln of 2. So this is a common handy thing to consider, like a common trick you can use. It's not really a trick, it's just the law of logs, but rather than doing natural log of 1/2, we can write it as natural log of 2, but negative natural log of 2. And that's kind of handy because now you can really see that k is a negative number. It's a negative number, which means that it's representing decay instead of growth. So you'll see that a few times on the homework in this lecture, just a few times. So I wanted to point it out explicitly. All right, now we know what K is. So now we know what K is. There we go. We can plug this into our formula. And this is a perfect time to use that other notation for the natural exponential function, right? So remember that this is e, it's e to the power. Maybe I'll even write this right now. So this is e to the power of negative ln of 2 over 1590t. But sometimes that feels a little bit messier than just writing exp, using the other notation for the natural exponential function. But it's still the same thing. And this is what our model is. And the cool thing about this is we've entirely preserved equality so far. We've preserved equality. This is the actual model, so nothing has been approximated yet. We're still keeping the relative growth rate k precise. And now we can use this to answer the other questions. All right, so how much is remaining after 1,000 years? Well, we can plug in 1,000 to our model and then simplify, and then we're going to get about 65 milligrams. So after 1,000 years, there'll be about 65 milligrams of this radium-226 remaining. Now, to find how long it takes to decay to 30 milligrams, we're kind of inverting the problem. Now what we're saying is, if we know how much is left, how long will it take? Whereas before we were saying, how much will be left after this time? So we've inverted the problem now. And in that case, what we're going to do is we're going to set the output equal to 30, and then we're going to solve for the input, t. And here again, we're just going to use general algebra techniques and then properties of logarithms. So here we go. Set 30 to be the output of our model, and then solve for t. Move everything away from t. Write it in logarithmic form. That way you can get rid of the exponential, right? So you get this, and then we're almost to t at this step. So basically just divide both sides, or multiply both sides by negative 1590 over ln of 2, and we get that that's what t is equal to. All right, now's a good time to go to a calculator or some kind of computational resource and have it approximate, because in this kind of a situation, while this is an exact result from our model, in context, it would be nice to have something more meaningful to the human disposition. Like, how many years is that exactly? Or at least close to? Well, it's about 2,762 years. There you go. So according to this model, the natural law of decay, it'll take about 2,762 years for 100 grams of radium-226 to decay to 30 milligrams. All right. Okay, so that's radioactive decay. Now let's move on to Newton's law of cooling. Newton's law of cooling. Same kind of a setup. There's just a slight difference here. And this is a fun one because you can imagine it when you're just like sitting in your kitchen or looking at like a can of sparkly water in your fridge or something like that, right? So what Newton's law of cooling states is that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. So I want you to just kind of ponder this for a minute. So think about what that says just for a minute, and then we'll talk more about it in a second. Okay, so let's talk about it a little bit more. And this kind of makes sense if you think about it physically. So if you can imagine yourself sitting in your kitchen or sitting somewhere and you've got like, a cup of coffee, or you've got like a can of sparkly water or just a glass of ice water or something sitting around, right? What this law says is that the rate at which the object cools will be proportional to the temperature difference between the object and the surroundings. So it's not that it's proportional to the temperature, or I should say just the temperature of the object, like the coffee mug or something. It's proportional to the difference between the temperature of the object and the surrounding temperature. And that makes sense because, things will cool at a different rate depending on the temperature around them, right? If something is already cold and it's very cold around, then it's not going to cool very quickly, if at all, right? Or if something is very cold but it's burning hot outside, then the rate of change of the temperature is going to be large. It's going to be fast, right? It's going to go from cold to hot very quickly. So if we let T of T, you got to follow this, follow the notation here. T of T be the temperature of the object at time T, and T of S be the fixed temperature of the object's surroundings, then the law of cooling says that the change in temperature will be proportional to the difference between the object's temperature and the surrounding temperature. All right. One thing I want to point out here before I go to the next line is that we're assuming that the surrounding temperature is a fixed number. So this is something that you can change and adjust later on when you take a course in differential equations. But for now, just to keep things simple, we're assuming that the surrounding temperature is a fixed number. So it's not changing. Like you could think of it as the room temperature is remaining at 75 degrees or whatever, and it's not going to fluctuate at all. If it did fluctuate, so if you're wondering like, oh, what would the model look like if the temperature was changing, the surrounding temperature, you would just have a different function here. You would have another temperature function, a function that's dependent on time, and you would just have two different functions and you would continue that in that way. It just makes things a little more complicated, but we're going to assume that the surrounding temperature is fixed for our purposes. Now, what we're going to do is we're going to write y of t is equal to that difference, T of t minus T sub s. Then the derivative of y is equal to the derivative of t, because again, T sub s is constant, so when you take its derivative, it goes to 0. So this is dt dt. So once again, we can write this equation like so. And we have seen this exact model before. This is the natural law of growth and decay. There you go, or the law of natural growth and decay. So it is actually one of those situations. Now let's try it out. Here we go. Let's say a bottle of juice is sitting on your kitchen counter at room temperature. We'll say the room temperature is 72 degrees Fahrenheit. You put it in the fridge, which sits at 44 degrees Fahrenheit. And after half an hour, the juice has cooled to 61 degrees Fahrenheit. What's the temperature of the juice after another half hour? And then how long will it take the juice to cool to a crisp 50 degrees Fahrenheit? Okay, so this one I want you to try on your own at first. So start by just thinking about it. And honestly, you should reread this problem maybe like 4 or 5 times. So start with that. Just try to read this 4 or 5 times and just make sense of everything that it's saying. Okay, now say something out loud to yourself about how you will start working on this problem. What's a good thing to begin with? Maybe like a formula you could write down. All right, and now try to work it out yourself. See if you can use that formula we were talking about and see if you can fill in all the blanks, so to speak. See if you can construct a model first, and then we'll go from there. All right, here we go. So we know that Newton's law of cooling was given on the previous slide, and so if we fill in what we know already, we know this, right? So the initial temperature, or sorry, the surrounding temperature is going to be 44 degrees in our situation because we're putting the juice in the fridge. So we're putting this bottle of juice into the fridge, and the surrounding temperature of the bottle is going to be 44 degrees. So this is what we know outright. All right, so we're going to let y of t be equal to t of t minus 44, just like we did before. And then now we can look at the initial temperature difference. So one thing that's a little bit subtle about these questions is that we're looking at a temperature difference here, the difference between the temperature of the object and its surrounding temperature, right? So the difference is t of t minus 44. So at time 0, we have t of 0 minus 44. But remember, at time 0, the initial temperature of the object was 72, right? Here we go. So the juice is starting at 72 degrees Fahrenheit. That's its initial temperature. Then when we put it in the fridge, it's surrounded by a 44-degree environment, right? So the initial difference is 28, the initial difference. And so using that theorem, we can write our model as y of 0 times e to the kt. and we just found that y of 0 is 28. And remember, what is 28? 28 is, or I should say this number here, is not the initial temperature, and it's not the temperature of the surrounding environment. It is the initial difference in those temperatures. It's the initial difference in those temperatures, the difference between the temperature of the object and the surrounding temperatures. That's the key thing to recognize about these, is that this law is stating that the change in temperature is proportional to that difference. That difference. All right, now we've got the model, so we need to find K. We don't know what K is yet, but we are given some other information, right? So what is the other information? We're given that after half an hour, the juice has cooled to 61 degrees Fahrenheit. So from that, we can figure out, or I should say, from that, we can figure out what K is going to be. Here we go. So we know that 30 minutes, because remember the time is measured in minutes here. At 30 minutes, the temperature will be 61, the temperature of the bottle of juice, right? The bottle of juice. So that means that y of 30 is going to be that temperature minus 44, which is 17. Okay, so ponder that one as well, because there, again, there's a subtlety between what is the initial temperature and what is the initial temperature difference, and another subtlety here between what is this temperature and what is the temperature difference. So, and I'm just going to throw this up for just a moment here. Just ponder this for another moment. Think about it before we move on to the calculation. All right, now let's go through the calculation. There is the difference at time 30, so we set this equal to this, and then we can solve for k. Move everything away from k, write it in logarithmic form, or take the log of both sides, and then solving for k, we get this. Boom. All right, using a calculator or some kind of computational resource, we can estimate that k is about negative 0.01663. So that's the relative decay rate of the difference in the temperatures. All right, now we can add this to our model. So this is what our model is in completion once we've used this approximation. And so that means that the temperature at any given time is going to be this, right? The temperature at any given time is going to be that. Again, the reason for that is this is the difference in temperature, right? The difference in temperature. And what was y of t? Y of t is t of t, oops, minus initial. There you go. That's what that is. Okay, let's see. Okay, so now that we have this temperature model, we can compute what the temperature is going to be after another half hour. So after another half hour, the amount of time that will have passed will have been 60 minutes. So we can plug that into our model here and then approximate it with a calculator, and we get 54.3 degrees Fahrenheit. So after another 30 minutes, it'll have dropped down to 54.3 degrees Fahrenheit, about. Now, for the last part of the question, if we want to know how long it will take to cool to 50 degrees, again, we're kind of inverting the problem here, right? So we're going to set the output of the temperature function to be 50, and we're going to solve for the input, time. And this is just an exercise in algebra. Start moving everything away from t. Get everything away from t. So subtract 44, divide by 28, and you get this. Now you can convert it to logarithmic form or take the log of both sides, and you'll get that ln of this is equal to this. Divide both sides by this amount, or I should say this amount, and then you get an equality for t, an equation for t. Now you can go to a computational resource, calculator, and you'll get that t is about 92.6. So that means it'll take about 93 minutes for the juice to cool down to 50 degrees in the fridge. Right, pretty cool stuff, right? It's kind of cool. So this this is like a good taste of how you can do these relatively simple physics problems when you just have even a little bit of calculus, right? Calculus just opens up doors, opens up worlds. It's really fun. All right, last thing we're going to talk about, and we're not going to spend a ton of time on this one. We'll do more of this in the activity when we do the activity together. But let's talk about continuously compounded interest. So if you've got an initial amount of money, A sub 0, and you invest it at an annual interest rate R that's compounded n times per year, then after t years, the value A of t will be given by this formula. So this is a formula that some of you may have seen before in a pre-calculus class or an algebra class or even like a statistics class or a business class. This formula is pretty popular. I won't go into the details of why the formula looks that way, but if you're interested, just ask me and I can pull up some slides that show where this formula comes from and why the formula looks like this. But for now, we're going to assume that this is the actual formula. So I'm hoping you've at least heard about it at some point. Now, as the number of compounding periods increases, the interest paid increases because interest is being added to the initial investment more often. So a simple intuition here is that if you increase the number of compounding periods, then you're going to make more money, right? Because the bank is essentially, or whoever is essentially adding more interest, money earned from interest to that initial amount more quickly, or more often, I should say. So if they're adding it more often, you're going to make more money and the amount is going to increase more quickly. So if you let the number of compounding periods go to infinity, then the interest is compounding continuously compounded interest. And this means that the interest is being compounded at every moment. So basically at every moment in time, interest is being added to the original amount every moment in time. All right. So how do we model that? Well, maybe you can kind of see what's going to happen here. We're going to let n go to infinity and see what this formula becomes. That's the idea. So this is what we'll have. We know that the amount will be this limit instead because we're going to let the amount of compounding periods increase to infinity. So the way that we're going to evaluate this limit is through a little bit of cleverness, a little bit of substitution. So the first thing we're going to do is this. Let me zoom in a minute. We're going to rewrite the exponent, too close. There we go. We're going to rewrite the exponent nt as n over r times rt. So really what we're doing is we're using one of the most powerful techniques in mathematics, which is multiplying by 1. There are two most important or two most powerful techniques in math. The first one is multiplying by 1, and the second one is adding 0. So just with those two techniques, you can get an incredible array of results. You can prove the fundamental theorem of calculus using this basic algebraic technique, almost like an arithmetic technique. And we're going to do it right here. Multiply nt by 1, except we're going to write 1 as r over r. R over r. And there's a reason for that. There's a reason for that, because now what we can do, let me go down a little bit. Here we go. Now what we can do is we can pull things apart, but what I'm trying to make happen is I'm trying to make a pattern connection between this exponent and this number right here. You see how this is r over n and this is n over r? That means one is the reciprocal of the other. R over n is the reciprocal of n over r. And just using properties of exponents, we can pull out the rt right to here. So that's just properties of exponents there. Now, because of linearity of the limit operator, we can actually move the limit operator in front of this constant. So we can pull the original amount out to the front. That's just a fixed initial amount of the investment. And then we can rewrite the limit like so. So here's another little bit of cleverness. We're going to let m equal n over r. So if m is n over r, then n over r here becomes m. And r over n becomes 1 over m, because r over n is the reciprocal of n over r. There we go. So really what we're doing is we're just kind of massaging this formula so that we can get it into the form of a limit that we have seen before. What is that limit? It's this one. The limit as m goes to infinity of 1 plus 1 over m to the m. Well, guess what that's equal to? That's equal to e. That's equal to that number, that special number e. So there we go. Now we have the formula for continuously compounded interest. There it is. So if our interest is compounded continuously, then the amount of the investment after t years is given by that formula, a naught times e to the rt, where a naught is the amount of the original investment and R is the annual interest rate. Cool stuff, huh? I think it's kind of cool. It's cute how E just pops up. All right, so on that note, let's play. So that's it. We're not going to do an example of continuously compounded interest in the lecture. I'm sure you could imagine similar examples in terms of the mathematics that we would do. They would pretty much be the same as what we saw in the previous examples. You can solve for time, you can solve for amount, you can plug things in. We'll do that in the activity, but if you'd like, you can also read the book and they will have some other examples there. Now, before I ramble on too long, I'll just end there and say thank you again, and I will see you next time.